Alright, so now let's talk about graphing. So what I've done here in part 2 of this ping pong ball lab is I have filled out my data table with the first 5 frames of this simulation. So I've gotten the distance or position and the time at each of these frames, starting at 0, 0, and it's given me this graph. Now the shape of this graph is linear, and again I'm going to post a reference table to the shapes of graphs and matching them to their names. And the reason we have to know that is because I need to curve fit this graph. So the goal of any physics lab is to make a graph, and if it's a line, you're going to have to draw the line. So Pivot's going to do that for us. I'm going to hit curve fit, and it's important to note that this is linear, so I choose the right curve to fit it on. And you notice as soon as I hit it, boom, line is drawn. Not only is a line drawn, and it does line up pretty well with our points, that's one of the questions, there's a box down here, and there's some numbers in this box. The main point of this video is what do I do with these numbers, because this is where we're actually getting our information that's going to help us answer our questions in later labs. So if I look at this box up close, you see y equals ax plus b. That is the equation for a line where y is your y variable. A is your slope. You may have remembered this line equation as y equals mx plus b. So our m has turned to a. So a is going to tell us the slope. B is our y-intercept. Where does it cross the y-axis? This is probably going to be some initial value for us in later equations, depending on the graph, depending on what the equation is, what we're looking at. So let's first figure out, how do I know what a is in terms of a number? So I look at a down here, and I see 2.029 e plus 4 plus minus 107.6 centimeters over seconds. That is computer speak, and the computer is trying to tell you a number here. So how do we decipher that number? Well, let's go from right to left. Centimeters per second, that is just the units. So I'm going to leave that there. This tells me what is this number measured in, and it also gives me a clue about what that number actually means. If I see a distance over a time unit, I automatically know that, and I'm sorry, I'm drawing with my mouse here, so it's pretty bad. This is going to be, I'm not even going to try, that's worse. That would be the speed, and I know that because the units are distance over time, centimeters over seconds. This plus minus 107.6, whenever you see a plus minus, that means that this number is basically our margin for error. We had to guess on some of our position measurements, like the 15.8, the 31.3 I had. So this is basically saying the true value could be 107.6 above our number or 107.6 below. So that's just our pretty much our error and our uncertainty. What are we going to do with that? We are going to ignore it. Take it all off. So I'm going to keep doing this until it's gone. So I'm not worried about that number. So what about the rest here? This 2.029 e plus 4. Well, when a computer puts e in a number, and I'm going to try to draw this with my mouse, that means that is an exponent, but it's a very specific exponent. It means times 10. Now the plus 4 means that my exponent is positive, and that is a 4. And so the e plus 4 means times 10 to the 4th power. So I know I'm looking at some scientific notation here. And I know I've got 2.029. Again, sorry, this looks like a 3-year-old drew it, but that's okay. So now, this is something we probably can work with. We recognize how to read this number, but if you have to type this as an answer, I don't want to have to type times 10 raised to the 4th power. So again, quick review, how do I make this a number that's not in scientific notation? Well, times 10 means I'm going to be moving the decimal. How many times am I going to move the decimal? 4 times. What direction? This positive here tells me my exponent is positive, so I'm going to move that to the right 4 times. If you move the decimal to the right 4 times, you get 20,290. So I know what A is. It's 20,290. This should be pretty close. If you found the speed in part 1, this should be pretty close to that speed. And that makes sense because this is a speed. We're finding the same value using two different methods. So how do I make this equation fit our specific graph? Well, if you look at the graph on the Pivot Lab, the y-axis is telling me about the ball position. So the ball position we're going to signify or symbolize with x. And it'll become clear once we start watching videos why we're using x for our ball position. A, we just found the number, was 20,290. And then what is the x-axis of my graph showing me? It's showing me the time that has passed. So instead of x, I'm going to write t. And I'm going to write my t's with a little curly at the bottom so that you can differentiate what is a t and what is a plus. I could write plus here, well, if I had room on this little board, but it's going to be plus 0 because I know my y-intercept should be 0. Why does it not look like it's 0 here? Well, that's because I had to guess some of those position values, so the line that was drawn could be a little off. But for us in physics, this is close enough to 0. If I know it should be 0, we're just going to say it's 0. So that's how we use it. We make a graph, we curve fit, and the main thing we should really focus on is how do I read this little box that comes up when I do a curve fit. So I hope this video is helpful for this lab, but also future labs in determining what are our values and how to read and get, a nice number out of the gibberish computer speak that pops out. So I hope this is helpful. Again, remind me with any questions.